This time around, we're going to take a look at the natural logarithm function. And basically, we just want to learn how to work with logarithms whose base is the number e. So this is likely the first time that you've been introduced to the number that's denoted with a lowercase e. So we'll talk about that for a little bit at the same time. So recently, we've been studying logarithms. So we first started with a definition of a logarithm. And basically, we found out that a logarithm is equivalent to an exponent, mainly from this definition, which said that x equals b to the y is exactly the same thing as y equals log base b of x. Y was the exponent, and over here, y equals the log. So logs are essentially exponents. So we call this exponential form, and we call this logarithmic form. So if you want to write it using a log, you can do this. If you want to write it without the log, you can write it this way. And b, in our definition, b is the base, and it can be any positive real number as long as it's not positive 1. And again, we don't want b to be positive 1 because 1 raised to any power is just 1. So that's pretty boring. It doesn't really do anything for us. So what we want to do now is we want to look at a base that, along with 10, which we called a common log when the base was 10, there's another base that's used quite a bit in math and science besides 10. I mean, the base can really be any positive number besides 1, but prior to calculators, base 10 and this new base were used quite often. Were kind of the two bases that most people ended up using for one reason or the other. Well, in math already, you've learned that the symbol pi represents an irrational number that's approximately 3.14159, and then the decimals go on and on and on. They never terminate, and there's no pattern to it. It's an irrational number. So pi, you cannot represent the number pi using two integers being divided. So you can't write pi as two integers that are being divided. It just can't happen. That's why we call it an irrational number. Well, in mathematics, lowercase e is also an irrational number. E is approximately 2.71828, and then the decimals keep on going. They don't terminate, and there's no pattern to them. So when you see lowercase e in mathematics, that can represent an irrational number that's approximately 2.71828. So e and pi are very similar. We use a symbol to represent the actual irrational number, and then you can run both of them through a calculator to see how, get more and more decimals of them if you need more decimals than what I've given you here. So it's going to be weird. You got to train your brain to recognize lowercase e in mathematics to be a number, like pi is a number. So e is approximately 2.71828. Now, naturally you might think, well, where did this number come from? Well, the definition of this number is a little bit more difficult to explain than pi was. So pi, you just take the circumference of a circle, divide by the diameter, and out pops pi every time. So, any in geometry, it's pretty easy to kind of walk you through where pi comes from and explain, its origination. E, on the other hand, requires a little bit more sophisticated mathematics to give you a good explanation as how we knew this number existed and where it came from and why it's useful. So in pre-calculus, um, I show the students a pretty easy to follow, relatively speaking, easy to follow, um, argument for, how E kind of popped out of nowhere and how mathematicians may have stumbled across it. But the actual definition requires limits, which is something from calculus. So I'm not going to go through that in this video, but if you're curious, just let me know, and in class we can, I can kind of give you an easy to follow, argument for where E comes from. So we can do that in class if you need it. Well, E for us right now, we just need to recognize that E is an irrational number that's approximately 2.71828. So E, since it's a positive real number, it can be the base of a log. So if this number E is the base of a log, we call that the natural logarithm function. So if the base is E, then we call it a natural log for short. Well, most people do not write, if the base is E, most people do not write log with a little e down here. They usually write ln instead. So they mean the exact same thing. So anytime you see ln and then some number after it, that's a natural log. But it's really the exact same thing as log base e. Personally, I don't care which one you use. You just need to be aware that textbooks and standardized tests and college mathematics, they're all going to use ln instead of log with a little e written below it. But as far as your work goes or what you write down, either one's fine. Now, ln, it seems weird. Why did they use ln when it's called the natural log function? Well, remember, most of the mathematics you study in high school was not discovered by English-speaking people. So ln comes from, I believe, the Latin logarithmus naturalis, I think. That's close, if not correct. And so back when this was discovered, that's how this was represented as logarithmus naturalis, so ln instead of natural log like we say now in English. But since it's a log, everything works exactly the same way. X has to be a positive number. We only do logs of positive numbers. If you do the log of a negative number, it comes out imaginary, and we're not doing that. And then y can be any real number. So it turns out, the range of a log function is all real numbers. So there's really nothing new here other than the base is this number e. So that's really, there's actually nothing new here. Everything you learned about logs is still true. It's just the base is this number e. All right, so since there's not really anything new, let's just kind of look at some of the problems we've been doing, but just get comfortable with the fact that the base could be e. So for example, what if we want to write these in exponential form? So right now they have logs. So natural log of x equals 5. You got to remember that's the exact same thing as log base e of x equals 5. So ln of x is the same exact thing as log base e of x. Well, we want to write it in exponential form, so we can do the circle thing that we talked about earlier if you would like, if that helps. So it'd be e to the fifth equals x, and that would be exponential form. So natural log of x equals 5 is the exact same thing as e to the fifth equals x. This is log form, this is exponential form. Remember, e is about 2.71828, so x is about 2.71828 raised to the fifth power. Now that would be an approximation because e is actually an irrational number, so there's an infinite number of decimals. Let's try it again. So natural log of e squared equals 2. Well, you could write it as log base e of e squared equals 2. And then again, if the thing is helpful, then it would be e squared equals e squared. So that would be exponential form. So for this one, natural log of 11 is approximately 2.398. Well, you could write this as log base e of 11, because that's exactly what ln of 11 means. And then you can do the circle thing. So e to the 2.398 power is approximately 11. So there's nothing new here. We've done this before with other logs with different bases. We're just the base is e now, which is kind of weird because e is a number. So we just want to practice with e and get the hang of it. Well, let's go the other direction. So what if you already have exponential form and you want to introduce the log? So for this first one, e to the 1/2 is equal to the square root of e. That's true. So we want to write this as a log. Well, here's the base. This is the base. And then we have our exponent of a half. So it'd be log base e equals 1/2. And then the square root of e, that has to be the argument of the log. But like I said earlier, no one really leaves it log with a little e down here for the base. They write ln instead. So the natural log of the square root of e is 1/2. So that would be log form. So this was exponential form, this would be log form. For b, we'd have log base e of 1 equals the exponent 0. But again, no one writes log base e, or it's very uncommon, let's put it that way. So we'd write natural log of 1 is 0. Which makes sense, because no matter what the base is, when you raise it to the 0 power, you always get 1. So one more time, the base is e, so it would be log base e of 1 over e squared equals the exponent -2. But using ln, it'd be natural log of 1 over e squared equals -2. So exactly how we converted it before. All right, so you should be able to do some logs without a calculator, some natural logs without a calculator. But you're going to find out that quite a few natural logs we wouldn't know off the top of our head. We're going to have to use a calculator. So for a, we have the natural log of e to the 7th, and we want to simplify that. We want to know what that's equal to. So, we want to figure out what is this thing equal to. So this would be log base e of e to the 7th. And then you can do the circle thing if it. So e to what power is the same thing as e to the 7th? Well, it has to be the 7th power. So what that tells me is the natural log of e to the 7th is really just 7. So let's check that. Let's check that on our calculator. So on your Inspire, on the left-hand side, you should see a little ln in light blue. So we hit the control and then the ln, and we want to see what the natural log of e to the 7th is. Well, E is the button right below natural log. So we press E, whoops. So E, and then to the 7th, and then we press enter, and we get 7. So natural log of E to the 7th is 7, which is what we had right here. So we end up with 7. So let's try it again. Natural log of the cube root of E squared. So we want to know what's that equal to. So that's log base E of the cube root of E squared. And then if you convert it to exponential form, so e to what power equals the cube root of e squared? Well, the cube root of e squared is e to the 2/3 power. So x must have been 2/3. So this must equal 2/3. So the natural log of the cube root of e squared is 2/3. So let's try that one. Let's check that on the calculator. So the natural log of the cube root of e squared is 2/3, just like we had. So let's try one more. Natural log of 14. So this equals some number. So that would be log base e of 14 equals some number we don't know. So if we convert that to exponential form, what power is 14? Well, e is an irrational number. It's a decimal. It goes on forever and doesn't repeat. So I can't change 14 to be base e. That's not going to work. So e to what power is 14? We're not going to be able to get a high degree of accuracy for that without the use of a calculator. So one like this, there's not really a whole lot we can do without using a calculator. So we don't know what power that is. So the natural log of 14, we're just going to have to type into a calculator and see what that is. So natural log of 14, and we'll hit Control Enter to approximate it. It's about 2.639. So it's about 2.639. So it turns out e to the 2.639 power is about 14. About 14, because we had to round it. So sometimes, we have to use a calculator to simplify a log and see what it's equal to. All right, so the log properties the laws of logarithms that we learned earlier, they still apply, even for these logs, because they're still logarithms. So when you see 2 natural log of 5 plus natural log of 4 minus 3, for example, and we're supposed to combine this up to a single log, well, if it helps you, instead of using the ln, you can write this as 2 times log base e of 5 plus log base e of 4 minus, well, 3 doesn't have a log in it, so we're going to have to write it using logs. So 3 would be the same thing as log base e of e cubed. So we saw that earlier. If you have log base e of e to the 7th, since this is base e and this is a base e, then 7, that's what that simplifies to. So 7 is the same thing as log base e of e to the 7th. So 3 is the same thing as log base e of e cubed. And then we can take our coefficients and we can move them up to the exponent. So log base e of 5 squared plus log base e of 4 minus log base e of e cubed. And then we have 2 logs that are being added together, both with the same base. So they combine to be 1 log. And then you multiply the arguments. So it's going to be 5 squared times 4 minus log base e of e cubed. And then now we have 2 logs that are being subtracted with the same base. So those combine together to be 1 log, where you divide the arguments. So 5 squared times 4 is 100 divided by e cubed. Well, again, we don't want to leave log base e. We'll write it how it's usually written. So that'd be natural log of 100 divided by e cubed. So we've combined these 3 terms into a single logarithm. Well, we can also solve equations just like we did with other logs. The only difference here is the base is e. So if you have natural log of x equals 2, that's the same thing as log base e of x equals 2, and then you can do the circle thing. And squared equals x. So our solution is the set of all x such that x equals e squared. Remember, e squared is just a number. So e squared is about 7.389. So it's weird because when you see e, you don't think of a number, but in mathematics it actually is a number. So e squared is 2.71828 squared, which is 7.389. Let's try that again. So this would be log base e of 1 over x equals 2. So e squared would be 1 over x. Multiply both sides by x, and then divide. And x is 1 over e squared. So it would be the set of all x such that x is 1 divided by e squared. Let's do one more. So this one we have an exponential equation. So e to the 2x equals 9. Well, I'm not going to be able to rewrite 9 so it has the same base as e. So let's switch it back to a log and see what happens. So it'd be log base e of 9 equals 2x. Divide by 2, or multiply by a half, would be the same thing. And then if I put the 1/2 back up as the exponent, 9 to the 1/2, that's the square root of 9, the principal square root of 9. So we get log base e of 3. And log base e, remember that's a natural log. So my solution is the set of all x such that x equals the natural log of 3.